In this video, we're going to take a look at finding torque on an object that's not lined up, and this looks a little bit different than when we looked at torque from before, and it's helpful to look at torque this way um, in terms of what we need it for looking at the ladder. So here's a picture of the ladder. We'll go ahead and draw the force of gravity in the middle, just like we normally do. And we'll say that this is 60 degrees and the length of the ladder is 8 meters. So what we did before to figure out what the torque would be like, we'd have to know the axis, and so for these problems we'll use the base as the axis of rotation, and then uh, essentially what we did before is we tried to figure out the force that was perpendicular to the ladder. So we already know this force of gravity is going to cause a rotation like this. So it'll be a clockwise rotation. But the force and the lever arm aren't lined up. So what we would have to do is this, and this is the old method. We would have to find the force here, and that force, which is perpendicular to our lever arm here, would be the force that we would need. And so this being 60, this would be 30 inside here, so then this would again would be 60 inside this one, and so we would have to use the cosine. SOHCAHTOA. So the cosine of 60 equals the adjacent, which is the force that's perpendicular to the ladder there, times the hypotenuse. And in this case, the force of gravity, and we'll say the mass is 120 kilograms. So mass times 9.8 will give us the force of gravity, and that is 1,254.4 newtons. And so this force that's perpendicular would end up being 627 newtons. So to find torque, force times the lever arm, and we already, sine theta, we already did this part with the trig. And this would come out to be the half of the ladder is 4 meters. So from here to here, 4 meters. And 627 newtons times 4 meters will give us a torque of 2,508 newton meters. Okay. There's an easier way and a more effective way in terms of using a ladder. This other method is fine, but in terms of looking at a ladder problem like this where we can break it down, this is a lot, I don't know, I think it's a lot more intuitive to what we really need it for. So let's go ahead and do this. This, again, this whole thing is 8 meters. And cosine of 60 here. So the force of gravity, which is right smack in the middle, is also right smack in the middle of the base part here. Now what we're going to do to tackle this is instead of applying the trig to the force, we're going to apply it to the lever arm here. So what we're going to do is we're going to say this is our hinge, and we're going to use the original force of gravity. So we're still using the sine theta here with the angle, but we're applying it to the lever arm, not to the force. So in other words, this force of gravity is acting upon only this portion of the ladder that's perpendicular. So in this case, when we break that down, we'll find that the length here is 60 degrees, 8 meters. The adjacent side here, cosine is adjacent over hypotenuse. So the base of this be cosine 60 equals adjacent over the hypotenuse. So that'll be 4 meters. So half of that is 2. So 2 meters from here to here. So from this spot here to the hinge is 2 meters. So that's our lever arm, and then the force of gravity is that 120 times 9.8, and that is the 1,254 newtons. So now here, when we calculate torque, again it's force times lever arm times sine theta, and we applied the trig to the lever arm instead of the force this time, and we've got the force 1254 times 2 meters now, and we get the same thing, 2508 Newton meters. Now you may say, you know, well, why don't we just kind of solve it with this first method? The reason is, as we're adding more things and you know, let's say there's a person on the ladder, let's say we're looking at the force of the wall, it's going to be important to be able to break it down that way. So let's go ahead and take a look at what happens with the wall here. I'll do that in purple up here. And as we saw in our lab, as you guys did that, this is the force of the wall coming out. This wall is pushing back like this. And so let's go ahead and solve that with the method that we just did. We know that this force is acting upon the ladder, and it's going to cause a rotation like this, right? But the force and the lever arm don't line up. So what portion of the lever arm, which is the ladder, needs to line up with the force? It's this part of the ladder. Not the whole thing. The whole 8 meters is not, right? But the portion, this portion that's perpendicular is right here. So when we solve for that, 60 degrees, this is still 8 meters, and we can use our trig for that, and sine of equals opposite over the hypotenuse, and the sine of 60 equals the opposite side divided by the hypotenuse, is 8 meters. So this side is 6.928 meters. And now we can, now our force and the lever arm, which is the ladder, well, that portion of the ladder that's going to be affected, we can do that. So torque equals force times displacement times sine theta. And we already took care of the trig here because we found the lever arm. So our force, and finding the wall force, sometimes that's what we have to solve for. In this case, for this example, it's 70 newtons, and the lever arm is 6.928 meters. And when we calculate that out, we will get 484.974 Newton meters. And if we use this, you know, the method that we first used, you could, you know, we essentially could find out, you know, what portion of the wall force is perpendicular to that 8 meters, and then use the trig for that. But this is definitely, yeah, just definitely an easier method as we're solving this problem. So this is the first step in really understanding the dynamics with structures similar to a ladder.